Quantum random access memory. Probably you're familiar with a data type called a dictionary that is more generally known as an associative array. The dictionary consists of a collection of key-value pairs, where each pair maps the key to its associated value. Each data item is attributed to a certain key or address and can be accessed by calling the key. This kind of encoding can also be done on quantum computers. In classical computers, random access memory, or RAM, is a type of volatile memory that has memory addresses J and stores the binary data corresponding to each address. Suppose we have two quantum registers, J, which contains addresses, and D, to store the data. The quantum random access memory operation returns a superposition of data in a data register D correlated with address register. The index J means that D jth is the content of jth memory cell. Cats represent not single qubits, but the whole address and data registers. To address 2 to the power of n memory cells, the QRAM uses a superposition of n qubits for the address register. The size of the data register depends on the data itself. The following example shows how to prepare QRAM state. We want to encode the dataset D, which consists of two numbers, 1 and 3, into QRAM. We will use the basis encoding to encode the data. Therefore, we need to convert the data elements into binary numbers. The largest value in the dataset is 3, which corresponds to 1, in binary representation. Therefore, we need 2 data qubits. So, we need to encode 0, 1 state of the data register into state 0 of the address qubit, and state 1, 1 into the state 1 of the address qubit. The length of the data array is equal to 2. Therefore, we need 1 qubit for the address register. In accordance with definition of QRAM, the quantum circuit, which forms the connection between our dataset and the states of the address qubit, should result in the following state. The indices A and D indicate the address qubit and the data qubits correspondingly. This means that when the address qubit is in the state 0, the data is automatically in the state 0, 1. And when the address is in the state 1, the data is in 1, 1 state. The encoding of 0, 1 state of the data register into 0 state of the address qubit can be realized via the following quantum circuit. Indeed, if we send zeros into the input of this quantum circuit, the output will be state 0, 0, 1. The encoding of the 1, 1 state of the data register into state 1 of the address qubit is realized via application of 2 subsequent CNOT gates. This quantum circuit returns the state 1, 1, 1 if only the address qubit is in the state 1. Now we combine 2 considered quantum circuits and apply Hadamard gate to the address qubit in the beginning. The first qubit will be used for the address encoding, and the next 2 qubits for the data. The initial state of each qubit is 0. First, we prepare a uniform superposition of address qubit by applying a Hadamard gate. At this moment, it is convenient to rewrite the state of the system as a linear combination of 0, 0, 0 and 1, 0, 0 states. The application of first X gate flips the state of the first qubit. This operation doesn't really change the state of the system. Next, CNOT gate flips the second data qubit if the address qubit is in the state 1. The second X gate flips the state of the address qubit. After the execution of this part of quantum circuit, the state 01 of the data register is already encoded into the state 0 of the address qubit. The last part of this quantum circuit, two CNOT gates, flip the data qubits if the address qubit is in the state 1. This operation encodes the state 11 of the data qubits into the state 1 of the address qubit. Finally, we prepared the QRAM state for our dataset. When the address is 0, the data is equal to 01, and when the address is 1, the data register is in the state 1, 1. Probably you are wondering, why did we apply the first X gate? It didn't change the state of our system. To understand it, let's swap these two parts of quantum circuit. We again prepare a uniform superposition of the address qubit by applying a Hadamard gate. Then, two CNOT gates encode the state 11 of the data register into the state 1 of the address qubit. This time, the first X gate flips the state of the first qubit, and the state of the system really changes. CNOT gate changes the state of the data qubit if the state of the address qubit is equal to 1. And finally, the second X gate flips the state of the first qubit. We again prepared the QRAM for a given dataset. Basically, when X gates are applied symmetrically to the CNOT gates, when assigning some data element to certain address, the data can be encoded into QRAM in any order. The prepared QRAM can now be used in various quantum algorithms, such as the HHL algorithm or Groover's search.